In the spring of 2021, a standard operational routine came to an abrupt halt. The aircraft involved was a B-17G bomber known as Aluminum Overcast. The investigative operation did not begin in a remote debris field or at the bottom of an ocean. It began on a paved flight line in Florida, with the immediate grounding of a 36,000-pound aircraft. The stakes were procedural and absolute. A physical discrepancy appeared on the exterior of the airframe during a walk-around inspection. The visual evidence was isolated, but the structural implication was catastrophic. The ground crew identified a physical shift in the geometry of the left wing. The gap measured approximately 2 inches. This single measured dimension triggered an irreversible decision to halt all flight operations and lock the aircraft down. Flight operations for a heritage bomber operate under strict procedural boundaries. A pre-flight inspection is a rigid protocol requiring crew members to physically verify the condition of the exterior skin, the control surfaces, and the primary structural joints. The human eye is trained to look for missing rivets, fluid leaks, or misaligned panels. The wing of a B-17 joins the fuselage at a massive structural root. To streamline airflow over this critical joint, the original manufacturers utilized a metal fairing. A fairing is an aerodynamic cover. It carries no flight load and simply smooths the transition between the wing and the main body. It is designed to sit perfectly flush against both surfaces. During the walk-around, the crew noticed the fairing on the left side was no longer sitting flush. It had visibly pulled away from the fuselage. The displaced fairing was a visual warning, not a diagnosis. A fairing can loosen or deform for several reasons, but a gap of that size demanded immediate inspection of the structure beneath it. What appeared to be a superficial exterior anomaly could be the first visible sign of a serious internal problem. The bomber's approximately 34,000-pound empty weight means gravity is constantly loading the airframe. On the ground, the main landing gear carries loads into the inboard wing structure and through the wing roots into the fuselage. In flight, those same joints must transfer aerodynamic, maneuver, and gust loads while keeping the structure within its design tolerances. A 2-inch displacement on the ramp was far outside normal alignment and demanded an immediate structural investigation. The loads of flight could be substantially greater and more complex than the static loads present on the ground. The crew faced an immediate and localized decision trade-off. Continuing the flight schedule and ignoring the gap risked a catastrophic in-flight structural failure. Grounding the aircraft meant stranding a massive and complex machine far from its heavy maintenance base, with no immediate path for repair. The decision was dictated by strict evidence discipline. You do not fly an aircraft with an unexplained gross structural deformation. Competence under constraint means trusting the physical evidence over the operational schedule. That decision shifted the problem from flight operations to structural diagnosis. The displacement was indisputable. However, the investigators could not see the actual failure mechanism. The wing root of a B-17 is a dense and sealed environment. The primary load-bearing components are hidden deep beneath the aluminum skin and the displaced aerodynamic fairings. The visual shift indicated that something heavy had yielded, but the exact mechanical failure remained completely unknown. Investigators could not determine from the outside if a steel pin had sheared, if a metal web had buckled, or if a structural mount had deformed under static load. The external geometry only proved that the left wing was no longer securely attached to the fuselage. The immediate grounding of the bomber eliminated the risk of another flight with an unexplained and potentially catastrophic structural discrepancy. With the aircraft secure on the ramp, the investigation moved into the sealed wing root. The internal architecture of a heavy bomber depends on a concentrated but distributed load path between the wings and the fuselage. Each inner wing panel of a B-17 uses forward and rear truss-type spars, each with upper and lower tubular cords. These members carry aerodynamic and ground loads into a series of terminal fittings and attachment points at the fuselage. The modular design allowed wartime factories to build major sections separately, but it also placed enormous long-term demands on a limited number of highly stressed joints. Inside the root, investigators encounter a complex intersection of dissimilar materials governed by strict dimensional tolerances. Forged steel terminal fittings are bolted within built-up aluminum spar cord assemblies. Those terminals connect the wing structure to corresponding fuselage fittings through separate attachment hardware. The loads are shared among several joints, rather than one universal fork and three-pin connection, and every fitting, fastener, and surrounding aluminum member must remain within tolerance for the wing root to carry flight and ground loads safely. The external visual discrepancy discovered on the ramp forced maintenance crews to open access areas and examine the left wing root more closely. In 2021, EAA reported a crack and damage associated with the left shear web and attachment area, serious enough that the aircraft could not return to flight. The exact extent of the steel terminal fitting damage was not yet publicly established. Determining that required deeper access and, ultimately, removal of the wings. By then, the fitting had spent decades carrying repeated flight, landing, and ground loads, but calendar age alone could not establish the cause of the damage. Fatigue, corrosion, stress concentration, prior repairs, and the aircraft's service history all had to be considered. The public record did not identify a precise crack initiation point or quantify the component's lifetime load cycles. The failure mechanism therefore remained under investigation rather than settled. One plausible concern was fatigue cracking near a fastener hole, where the geometry can concentrate stress. But without a published metallurgical fracture analysis, investigators could not state that the crack began at one specific edge, followed one exact path, or failed under tension alone. At this stage, the observed damage justified grounding and disassembly, not a definitive microscopic reconstruction of the failure. Finding serious damage in the left wing root was a critical partial success for the investigation. The evidence explained why the aircraft had been grounded, but it did not yet establish the complete failure sequence. Because the right wing used equivalent fittings and had lived through many of the same flights, its condition also had to be examined. Equivalent design did not mean an identical damage history, but it was enough to make the opposite side a priority. Visual inspection still had value. It could reveal surface cracks, corrosion, loose fasteners, deformation, and displaced structure before a complete break. Its limitation was access. Cracking hidden inside the steel terminal fitting and surrounding spar cord assembly could remain invisible from the outside. Investigators needed a method that could examine the concealed material without cutting apart the intact joint. Because dye penetrant reaches only flaws open to the inspected surface, and the FAA later found the existing procedure unreliable for cracks hidden inside the spar cord, the engineering team turned to approved non-destructive methods, including magnetic particle and eddy current inspection. One approved method was an eddy current bolt hole inspection. After the relevant fastener was removed, a calibrated probe could examine the wall of the hole for changes in electrical response associated with cracking. The method did not by itself prove the condition of the entire airframe, and a clean result at one location would not establish that every other joint was sound. At the right side fitting, a positive indication would show that the concern was not confined to the visibly damaged left side. A negative indication would reduce concern at that tested location without eliminating the need for broader inspection. The definitive bilateral finding came later. During the deeper investigation in 2023, after both wings had been removed, the FAA reported a complete separation of the left lower forward fitting and cracking in the corresponding right side fitting. That later discovery changed the engineering picture. The right side crack showed that the problem was not limited to one visibly failed fitting, but it did not prove that every spar or every attachment in the primary lift system was damaged. What it did prove was enough. Critical wing attachment structure on both sides required approved inspection and repair before flight could resume. Long before that full picture was public, the aircraft was already immobilized in Florida. The original left side damage meant it could not be flown to a heavy maintenance base, and the scale of the required access ruled out a quick flight line repair. The bomber remained grounded as the regional weather threat intensified. Time windows in aircraft recovery are usually dictated by access, equipment, and weather. EAA's decision to remove the wing transformed the documented left shear web and attachment damage into a major field maintenance operation. Removing the wing of a four-engine bomber in a field environment requires specialized lifting equipment, custom-built shoring cradles, and absolute physical stability. The wings are massive cantilevered lifting surfaces. They must be perfectly supported during separation to prevent shifting and twisting the main fuselage. The recovery team successfully initiated the stabilization phase by supporting the wings and unbolting the heavy mounting hardware. The initial operational plan was to perform a localized field repair inside a large host hangar in Punta Gorda. This required the aircraft to remain on jacks and wooden cribbing for an extended duration, while new structural components were sourced, engineered, and fabricated. This static posture created a severe environmental hazard geometry. A B-17 bomber possesses an enormous physical footprint even when partially disassembled. When a historic airframe cannot be quickly reassembled and flown away to safety, it becomes a static target for regional weather threats. Florida is defined by its geographic exposure to seasonal tropical cyclones. The risk constraint was absolute and unavoidable. You cannot rapidly evacuate an aircraft that is resting in pieces on jack stands, and you cannot easily harden a temporary field maintenance site to withstand extreme wind loads. The slow, methodical pace of forensic heavy maintenance directly collided with the fast-approaching reality of regional weather. The theoretical risk became immediate in September 2022, when Hurricane Ian tracked toward Punta Gorda and EAA personnel secured the aircraft in the hangar before leaving the site. Public accounts do not establish that every possible option had been exhausted or document the exact tie-down procedure. What is clear is that the airframe remained in place when the hurricane struck. When recovery personnel returned after the storm, they found the host hangar heavily damaged. Portions of the building had failed, and one piece of structure struck the bomber's tail, causing repairable damage. The aircraft had survived a dangerous event, but the public record does not support a measured near miss of inches, or a claim that the fuselage was almost crushed. The storm still changed the project's risk calculation. The Florida site could no longer be treated as a dependable long-term home for the repair. The project managers reassessed the long-term plan. EAA decided that the resources required for the next phase were more readily available in Oshkosh, and the hurricane damage reinforced the danger of leaving the aircraft immobilized in Florida. The move was therefore a deliberate extraction and relocation, not an immediate emergency evacuation. The operational question remained the same. How do you move a four-engine bomber that cannot fly? A heavy aircraft is engineered to occupy open airspace, not public highways. Moving aluminum overcast by road meant reducing its dimensions and protecting fragile structure against loads it was never designed to meet in service. EAA crews and specialized contractors spent several weeks separating the bomber at original or approved points, then lifting, supporting, and securing the major sections for shipment on several trucks. Custom handling equipment was required to distribute loads and protect the thin aluminum structure, but the public record does not document every crane movement, cradle design, strap placement, or supported point. With the major sections secured, the convoy began the overland relocation from Punta Gorda to Oshkosh. EAA confirmed the multi-truck shipment, but the exact permitted road distance has not been publicly established in the sources reviewed. Oversized load routing would have required coordinated permits, escorts, and bridge clearance planning, so the journey should be described without an unverified 1,300-mile figure. Arrival in Oshkosh placed the aircraft inside a specialized hangar where long-term restoration could proceed without Florida's weather exposure. With the airframe secured in Wisconsin, the engineering data from the damaged joint moved through official channels toward a broader regulatory consequence. Operational data from one aircraft can change the safety baseline for every machine that uses the same critical structure. The bilateral damage showed that the condition could exist or develop elsewhere in the fleet without proving that every B-17 was failing in the same way. The FAA treated the finding as an urgent structural safety issue, not as proof that every 1940s forging had reached an absolute age limit. The agency described its action as interim and sought inspection reports to better understand the nature, cause, and extent of the damage. In May 2023, it issued an airworthiness directive requiring affected aircraft to be inspected before further flight. This specific regulatory order established a hard constraint across the United States heritage bomber community. It applied to an estimated 18 affected airplanes on the United States registry. That figure described the domestic registry population covered by the directive, not the entire surviving B-17 fleet worldwide. Only a small number were then in flying condition, while others were under restoration or displayed statically. The directive did not revoke every aircraft's airworthiness certificate. It prohibited further flight until the required inspection and any necessary repair had been completed. The legal boundary was strict, but the compliance path was not limited to complete wing root dismantling. Operators could remove the wings and inspect all 8 terminal-to-spar cord joints, or use the approved eddy current bolt hole method after removing the most inboard fastener at each lower forward joint. The directive imposed a serious logistical and financial burden on museums and heritage operators, but the scale depended on the inspection method selected. For the expected bolt hole eddy current option, the FAA estimated approximately 25 work hours, not hundreds merely to reach the inspection points. A crack or corrosion finding required an approved repair before further flight, but did not automatically condemn the entire joint or render the fleet permanently unairworthy. As of May 2024, the bomber was on public display in EAA's Eagle hangar in Oshkosh, while long-term preservation and restoration options were still being evaluated. Any future return to flight would require an approved structural solution and substantial resources. But the reviewed sources do not confirm a final plan to manufacture complete replacement spars or newly forged terminal fittings. The aluminum overcast discovery did not create B-17 wing root oversight from nothing. A 2001 FAA directive had already required inspection and repair of terminal-to-spar cord cracking and corrosion. The 2023 directive expanded that baseline after the earlier procedure proved insufficient. The physical extraction is complete, but aging structure still governs any future operation. Investigators have identified a dangerous failure location and a gap in the earlier inspection regime, but the complete cause, fleet-wide extent, and long-term solution remain under evaluation. The final question remains open. Is this regulatory grounding the final operational chapter for these historic heavy bombers, or the beginning of a far more demanding baseline for 80-year-old engineering?